Hello everyone. I am Dr.S. Anbuselvi, Associate Professor of Chemistry, Sri Sharda College for Women, Salem. In this video, let us see hyperfine splitting and zero-fine splitting, that is, fine struct ESR spectroscopy. Before entering to the topic, let us first see what is fine splitting. Fine splitting describes the splitting of the spectral line of atoms due to electron spin and relativistic correction to the non-relativistic Schrödinger equation. Basically, there are two types of fine splitting. One is hyperfine splitting and the other one is zero field splitting. The zero field splitting is usually a larger effect. Here, the separation between the multiplets is larger in magnitude. It is seen in molecules and ion containing more than one unpaired electrons. Whereas the hyperfine splitting is a smaller effect. The hyperfine splitting is possible when a species contains even a single unpaired electron. Let us first see what is hyperfine splitting. We know that whatever may be atoms or molecules or ions all consist of nucleus as well as electron. We know that all having spinning character. So, there is an interaction between spinning electron and adjacent spinning magnetic nuclei. Because of that, the ESR spectral line gets splitted. Such a type of splitting is said to be hyperfine splitting. If a single electron interacts with n magnetically equivalent nuclei, the electron signal is split up into 2ni plus 1 multiplet, and here I is the spin quantum number of the nucleus. The hyperfine splitting can be used to provide lot of information. That is, it provides information regarding number and identity of nuclei, distance from unpaired electron, and interactions with neighboring nuclei. Let us see the hyperfine splitting in hydrogen atom. For hydrogen atom, there is single electron, unpaired electron. So S is equal to half. And MS equal to plus or minus half. For hydrogen nuclei, I value is half. Therefore, magnetic spin quantum number of proton, that is Mi, is plus or minus half. Based on 2ni plus 1 formula, two lines appear in the ESR spectrum because of hyperfine splitting. Now let us see how the two lines are appeared. See the figure B. See the figure. In the absence of applied magnetic field, the two ms value, that is plus of and minus of, are doubly degenerate. If you apply the external magnetic field, the degeneracy is removed and we get two energy levels, and the electron, if interact with hydrogen nucleus, each of these line again split into two energy levels as shown in the figure B. The splitting shown in B is due to hyperfine interaction, that is interaction between spinning electron and adjacent spinning magnetic nuclei. As a result, four energy levels are got and because of the selection rule, del Mi is equal to 0 and del M is equal to plus or minus 1. Two transitions are possible and we get two lines in the ESR spectrum. and the energy of each energy levels are obtained by using the formula E is equal to G beta H ms plus A ms mi. And the possible energies are also for each energy levels are shown in this slide. Here A is the hyperfine coupling constant, beta is the Bohr of the proton, ms is the magnetic spin quantum number of the electron. For SO3 NO minus anion, here nitrogen is only the magnetic equivalent nuclei for which I is equal to half. Therefore, Mi is equal to plus or minus 1 and 0. So, we get 3 lines in the ESR signal of same intensity because of hyperfine interaction. If the I value is greater than half, we get equally intense line, whereas I is less than 1, line intensity follow the Pascal's triangle. For this vanadilyl compound, I is equal to 7 by 2 for vanadium. Therefore, as per 2Na plus 1 formula, 8 lines are seen in the spectrum. The indices are determined by using this Pascal triangle. If I value is less than 1, we get different intense line. If I is greater than 1, all lines appeared equally intense. For benzene radical anion, since there are 6 magnetically equivalent proton which will interact with electron because of the hyperfine interaction, we get 7 lines in the ESR signal with intensity 1:6:15:20:15:15:6:1, and the ESR spectrum of benzene radical anion is displayed in the slide. For methyl radical, there are 3 magnetically equivalent proton. Therefore, as per the 2Na plus 1 formula, we get 4 lines in the ESR spectrum because of hyperfine interaction, and since I value for proton is less than 1, that is half, we get 4 lines with a different intensity whose intensity is 1:3:3:1. For deuterium nucleus, I value 1 and there is only one unpaired electron. So, as per the formula, we get 3 lines. Since I is greater than half, the 3 lines appeared with equal intensity. In the previous case, we have seen in the methyl radical, there are 3 equivalent proton. But here in the naphthalene radical anion, there are 2 different proton environment. In such a case, the splitting follow 2NaIa plus 1 and 2NbIb plus 1 if the proton is in 2 different environment. So, as per this formula, there are 4 alpha proton and 4 beta proton. Therefore, 25 lines are appeared in the ESR spectrum of naphthalene radical anion. In anthracene radical anion, the protons are in 3 different environment. So, as per the formula shown in this slide, 75 lines are appeared in the signal. For NH3 radical, since the unpaired electron interact with 2 different magnetically equivalent nuclei, that is nitrogen nuclei and hydrogen nuclei, therefore the ESR spectrum will consist of 12 lines for NH3 radical. For CH2D radical, the carbon is magnetically non-equivalent for which I is equal to 0. the hydrogen nuclei and deuterium nuclei involved in hyperfine interaction. So as per the selection rule, 9 lines are appeared. Similarly, in CH3O CH2, the CH3 proton is in different environment and CH2 proton is in another environment. Carbon and oxygen are magnetically non-equivalent nuclei. Therefore, these 5 hydrogen interact with odd electron. Because of hyperfine splitting, we get 12 lines ASR spectrum. Similarly, in bis salicylidimine copper 2, copper, nitrogen and hydrogen are magnetically equivalent nuclei. First, the copper split the ESR signal. For copper, I is equal to 3 by 2. So, because of copper, we get 4 lines. Then, each of the 4 line is splitted by the 2 nitrogen atom into 5 lines. And then, the hydrogen split the ESR signal. Here, not all the hydrogen split the ESR signal, only the H dash hydrogen, which is shown in the figure, only split the ESR signal. For that, there are evidence also. So, the hydrogen split the ESR signal into 3 lines. Totally, we expect 4 peaks, each split into 15 lines, but the ESR spectrum consists of 4 peaks, each split into only 11 lines. In detail, the splitting by copper, that is the copper nucleus first split the ESR signal into 4 lines, and each line is further splitted by nitrogen into 5 lines, and all these lines again splitted by 2 hydrogen, only 2 hydrogen, not all the 4 hydrogen, into 3 lines. Actually, we get 4 group, each split into 15 lines, but because of some lines overlap with each other, we get only 11 lines in the ESR signal. For my convenience, I explain only the splitting of only one line. Similarly, all the 4 lines which is splitted by copper undergo the same type of splitting. So, the ESR spectrum consists of 4 lines, each split into 11 lines. Pyrazine ion, here also there are two type of magnetically equivalent nuclei, that is nitrogen and hydrogen, which split the ESR signal. The nitrogen split the line into 5, and then the hydrogen nuclei split each of the 5 lines into again 5. Tetra-asa-naphthalene anion, here also nitrogen and hydrogen involved in hyperfine interaction with the odd electron. The hyperfine splitting is shown as in the slide. Now let us see zero field splitting. When a metal ion is placed in a crystalline field, the degeneracy of d orbital will be resolved by the electrostatic interaction, but the spin degeneracy will remain until the magnetic field is applied. That is, when a species contains only one unpaired electron, the spin degeneracy remains until the magnetic field is applied. But when a species contains more than one unpaired electron, the spin level may split even in the absence of magnetic field. This type of splitting is said to be zero field splitting. Let us see the zero field splitting in Ni2 plus and V3 plus, that is both are having D2 electronic configuration, both having 2 unpaired electron. So S is equal to 1 and Ms has 3 values, that is 0 and plus or 1. Let us see the first figure, that is figure labeled A. In the first figure, there is no zero field splitting. That is, in the absence of magnetic field, the 3 Ms values remain triply degenerate. And when the magnetic field is applied, the degeneracy is removed and 3 energy levels are obtained. And as per the selection rule, 2 transitions are allowed transition, and for the 2 transitions we require the same energy. So we get single line in the SR spectrum for the splitting shown in A, whereas in B, zero field splitting exists. That is, even in the application of external magnetic field, the energy levels get splitted. That is, Ms equal to 0 has 1 energy, whereas Ms equal to plus or minus 1 energy levels are doubly degenerate, whose energy is different from Ms equal to 0. Then, when we apply the magnetic field, these energy levels get split into 3 energy levels, and according to the selection rule, 2 transitions are possible, but the 2 transitions having different energy. Therefore, in the presence of zero field splitting, 2 lines are appeared in the ESR spectrum, whereas in the absence of zero field splitting, as in figure A, only 1 lines are appeared, which is clearly shown in this slide. That is, the first one is absence of zero field splitting, and in the second one is due to the presence of zero field splitting in nickel 2 plus or V3 plus ion, that is the system having D2 electron configuration. Then let us see the Kramer's degeneracy. When a species contains odd number of unpaired electron, the spin degeneracy of every level remains doubly degenerate. This is known as Kramer's degeneracy. For even number of unpaired electrons, the spin degeneracy may be removed entirely by the crystalline field. For Kramer's degeneracy, let us take Mn2 plus as an example, which is having D5 electronic configuration. So for which S is equal to 5 by 2. So Ms value is plus or minus 5 by 2, plus or minus 3 by 2, and plus or minus 1 by 2. So, in the presence of zero field splitting, for Mn2 plus, we get 3 doubly degenerate energy levels because of zero field splitting. And when the magnetic field is applied, each energy level gets split into 2 energy levels. Totally, we get 6 energy levels, and for which, according to the selection rule, 5 transitions are possible. But the spectrum is again complicated by hyperfine splitting. That is, the 5 unpaired electron interact with manganese nucleus. Therefore, hyperfine splitting arises. Because of hyperfine splitting, each energy level is further split into 6 energy levels. So, because of hyperfine splitting, there are 5 peaks, each split into 6 hyperfine components are observed for the Mn2 complex. Thank you.